All right, welcome back to the channel. Today we're going to take a look at another differential equation. Take a look at this one. It's different. We have the derivative dy dx embedded in the equation. The objective is to essentially try to solve for y in terms of x. So let's dive into this. Suppose I told you that dy dx was equal to x over y. What I'm going to do is I'm going to separate these parts of the derivative. Those are called the differentials. And I'm going to cross multiply. I'm going to say y dy equals x dx. So I put my x's on one side, my y's on the other. Well, look at these little differential parts. They're just screaming for an integral. In fact, usually an integral and a differential, they want to be together. They're very attracted to each other. They're bookends. And so if I was to integrate both sides, I would get y squared over 2 on this side. And the integral of x is x squared over 2. And I have to introduce my constant of integration. So look what we were able to do. We were able to come up with an expression of the original equation. Okay, well, why is that important? Because this lays out an approach or a technique for solving differential equations. This is called separable differential equations. You can separate the x's and the y's, group them, and then integrate on both sides. So let's take a look at our problem up here. This is what we're trying to do. What I'm noticing is this. I've got x and y, and I've got x squared, y squared. What if I was to do some dividing? So let's say I was to take this original equation, say I was to divide by x 2 times. I'm going to end up getting y over x dy dx, this is being timesed, equals 1 plus, well, that's going to be y over x all squared. Now, why is that helpful? Well, look, I have a y over x here and a y over x here. It almost feels like a new sort of structure. What I can do is substitute. I can say, okay, well, why don't we just convert? Why don't we take this equation, this differential equation, and take it to a new variable called z. Now, why is that useful? Well, watch. If I'm going to get rid of y, okay, I'm still going to keep my x, and I'm going to introduce the z. Sort of like I'm swapping out a y for a z is what's happening here. So what that means is my derivative in the differential equation, it has to be swapped out for a dz dx. I'm still going to keep my x as my independent variable. So that means I'm going to have to do some work on this. So if I differentiate, if I say dz dx, then I could take the derivative of the right-hand side using the quotient rule. So that's the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared, which is x squared. And so here what I could do, I know I'm going to have to substitute the dy dx out. So if I was to do a little bit of algebraic manipulation, I could say that's x squared dz dx. I'll move the y over. That's going to become positive y equals x times dy dx. Now, okay, well, I could divide out the x. So divide by x, divide by x, divide by x, and that isolates the dy dx. That converts it to x times dz dx plus, well, look at this. That's y over x. What's y over x? It's z. And then this becomes dy dx. So that's going to be z times dy dx, which is this right here. And I'm going to put that in a set of brackets. So x dz dx plus z, close your bracket, equals 1 plus z squared. Well, what I could do is bring the z through. That's going to give me a z times x times dz dx plus z squared equals 1 plus z squared. And that means the z squareds can cancel, leaving a z times x times dz dx equals 1. So watch what I do. These are all being times together. That's what you want for separable differential equations. So I'm going to now separate my differentials. So the dz is going to stay on this side. The dx is going to go over to the other side. I'm going to keep the z with the dz. The x is going to come over to the other side, become 1 over x dx. And voila, this is amazing because now I have my z's on one side and I have my x's on the other. And now I'm going to integrate. So I'm going to integrate this side and I'm going to integrate that side. I'm just balancing the equation. So the integral of z is z squared over 2 equals, well, what's the integral of 1 over x? You know it, it's ln x. So the ln of x. I'm going to introduce a constant of integration plus c. Okay, well this is good. Now, I took out a y, don't forget that z was y over x. So I kind of have to put that back. So that's going to become y squared over x squared. I'll put a 2 in the denominator, the 2 there, equals the ln of x plus c. Now they gave me these initial conditions, okay? They said that when y is 4, x is 1. So this allows me to get a particular solution. Now where y is 4, I'm going to put 4. So that's going to give me 16 in the top. Y squared is 4. X is 1. 1 squared, that doesn't do anything. Divided by 2 equals the ln of x, which is 1 plus c. Well, what's the ln of 1? You know it, it's 0. So that's 0. So that tells me that c is equal to 8. Well, this is kind of cool because now what I could do is take this equation that's back in x and y and I can put the 8 where the c is. So that's going to give me y squared over 2x squared equals the ln of x plus 8. And then I could isolate y squared. Often you want to either isolate y or y squared. So here y squared is going to be equal to 2x squared ln of x plus 16x squared. And I'm going to put a box around that. I'm going to take a look at it and see if it makes any sense to me. So this gives us a particular solution to this differential equation for the specific condition. It didn't appear to be separable variable differential equation. But because of the fact that we could substitute out y over x for z, this is known as a homogeneous differential equation. Homogeneous. And maybe you're learning them in your calculus class. Anyway, if you like this video, don't forget to slap a like on it. Don't forget to subscribe. Some of you are watching all these videos and you're not subscribing, so you're not getting updates. I'm posting almost every day, so don't miss out on these amazing videos. And I'll see you right back here in the next video.